In today's world, the term isolated communities are often perceived as serene, rustic, and are idealized through the lack of problems of the modern world. The reality differs from these stereotypical impressions. A problem often overlooked by the outside world is the difficulties faced when rural communities try to access medicine due to the significant travel required. The MS-621 UAV offers a unique solution in the delivery of vital medicine to the rural and isolated communities. We believe the focus should be on a low-cost product with short construction times and high speed to help rural communities thrive. When designing the MS-621, we went through several iterations before landing on one which met all design requirements. The first step in any design is to evaluate the customer requirements. Hence, design limitations and capabilities can be found in order to analyze constraints via design tools that would be imposed as a result of mission objectives. The design requirements are as follows. A range of 10 miles. Be hand launched. Land on either a hard runway or soft landing such as grass or sand. Flying in winds of up to 10 miles per hour with gusts of up to 12 miles per hour. Carry a minimum payload of 150 grams. Assembled in 2 hours. To take off and land using manual control and cruise using manual piloting or autopilot. These design requirements have been grouped into a subset of general key design requirements of structure, range of stability, and the autopilot. Key performance indicators have been linked to each group. Meeting key performance indicators would mean a successful design. These indicators would fare into the testing stage and act as validators to the MS-621's design. In the early stages of development, we focused on using Microsoft Excel to automate the early development process. This allows us to easily change variables at any point in the design. It helped us visualize what the aircraft was potentially going to look like before manufacturing took place. Ensuring the aircraft met all design requirements related to the structural integrity is one of the most important facets with the mission at hand. One of the aircraft's main characteristics is the capability of landing on hard or soft ground without damage. Multiple throws were made, varying the bank angle to see how the aircraft would fare in both soft and hard landings. Several designs were considered and it was found that the belly landing was most suitable. As you can see, the aircraft is more than capable of withstanding impacts from both soft and hard landings. Another indicator of structural integrity of the aircraft is whether the wing is able to withstand the maximum in-flight load of 1.2 kilograms experienced during gusts, which includes an additional 20% safety factor. This was measured through beam bending tests, loading the center point of the wing with specified loads. After several iterations, the chosen wing was found to hold the expected loads while weighing the least. Given the application of our drone, it must also be easy to assemble in remote areas within a 2-hour time frame. The use of foam for the structure definitely allows for this, as it does not require any specialist equipment to use. Additionally, the material is cheap, easily accessible, and lightweight. The video shown is one of our chief engineers building the aircraft within the 2-hour time frame. The MS-621's design comfortably accommodates all current avionics and payload. Space has been allocated so that the payload can be increased if required. This would be contingent on a more powerful motor, which is easily implemented through the iterative design process used. In order to stand any chance of flying the required 10 miles, the aircraft had to be longitudinally and laterally stable. Although simulations made on Simulink showed stable flight, this was not found during flight tests. To validate stable flight, measurements of how far the aircraft deviated left or right of the launch spot were taken. A landing spot which deviated less than 1 meters with the max takeoff weight would be deemed stable. The MS-621's flight tests showed the aircraft deviated 0.7 meters to the left. The required 10-mile flight is hard to prove without the propulsion system. Instead, glide ratio tests have been performed to suggest whether this is possible. It was found that a glide ratio of 10.5 would suggest the aircraft could fly the 10 miles. Measurements for the height of each throw and the distance from landing to throw locations were taken. It was found that the MS-621 boasts a glide ratio of 11.2 at the max takeoff weight of 1.25 kilograms. At this weight, calculations showed the MS-621 has a range of 12 miles, 2 miles further than required. With a cruise speed of 17.9 miles per hour, the MS-621 is capable of fulfilling the mission in only 35 minutes. With a drone required to reach isolated areas, the need for an autopiloted system capable of ensuring stability when beyond visual line of sight is vital. As shown, the MS-621 is capable of being manually switched from piloted control to fully autonomous flight. In order to test the autopilot, pre-flight checks were made to ensure all avionics were responsive. Flight tests were then performed to test the autopilot by throwing the aircraft from some bank and checking if the autopilot was able to correct the aircraft. Tests showed that there was not enough time for the autopilot to respond to inputs, hence further testing would be required. Nonetheless, the MS621 is capable of both remote and autopiloted control. Here are some design improvements and feature recommendations.